Welcome friends to the 7th lecture and module 2 on the online course on risk and reliability of offshore structures. So, we are talking about lectures on module 2 where we are focusing on reliability theory and structural reliability. We are talking today on lecture 7, which is continuation of the last lecture on reliability methods. So, I put this as 3. In the last lecture, we have been discussing about first order second moment method. We also said a case specifically where when the variables R and S are normally distributed, we gave equations and expression for finding out probability of failure. We also continued with the discussion on if R and S are log normally distributed, we said that the limit state function Z is now going to be given by L ln of R by S. Let us call this equation number 1, where Z is a normal variable and therefore, the probability of failure can be given by 1 minus phi of which we gave in the last lecture. Now, in this case delta R and delta S are coefficients of variation of R and S respectively. Now, we have been discussing for about two variables R and S, maybe one is the strength and one is the load. One can also apply this in a more generic form, one can generalize this for n number of random variables which will be denoted by x. So, let the random variables instead of 2 be denoted by a vector x. In that case, performance function is given by Z is equal to g of x. Now, one can now apply Taylor series expansion of the performance function about the mean value. So, applying Taylor series expansion of the performance function about the mean values, which is of course known to us. Z will now become, let us say, g of x bar, where x bar is the mean, plus summation of I equals 1 to n partial derivative with respect to ith variable xi minus x bar I plus half I is equal to 1 to n second derivative dou square g dou xi dou xj, one more summation. Let us change this to j xi minus x bar I x j minus x bar j. Okay, there are two summations here. Call this is equation number 4. Now, truncating the series only with the linear terms. The first order approximation of mean and variance can be obtained. Of z can be given by so z bar, that is the mean, which is g of x bar, and variance of the variable equation number 5, where x j is the covariance of x I and x j. Now, if the variables are assumed to be statistically independent, in that case the variance will be given by which I call as equation number. Now, in this case the partial derivative of the variable are obtained at the mean values. Of the variables. Okay. This is one of the comfortable method, one of the reliability methods which can be used either for a 2 variable R and S. Usually they are found to be normally distributed or log normally distributed for the data or the ensemble cases in offshore structures. It is also general in most of the cases. So, we have given you the equation for both the cases to find the probability of failure. Suppose if we really wanted to have a set of variables as a vector x, then one can follow this procedure to find out the expansion or the limit state function and so on. Now, let us look into the next method, which is also very useful in terms of finding the probability of failure. This method is called Haushofer-Lin method. Interestingly, while the Taylor series expansion is valid for nonlinear performance function, the safety index cannot be directly related to the exact probability of failure. There is a problem here. The estimate of safety index now shall be more accurate when all random variables remain statistically independent. Now, given the fact that the normal variables and the performance function are actually a linear combination of random variables, Hasseffer-Lind has provided an improved method to find the safety index. This is found to be better than that of the safety index obtained from the first order second moment method. Okay. So, now there are some salient points about the Hasseffer-Lind method. This method is centered on computing what is called as a design point. Now, the question comes, what is the design point mathematically? Design point is the minimum distance of the performance function from the origin. Which is actually the safety index for the case of normal random variables. With linear performance function. Now, let us try to explain the physical difficulty in this whole technique. Now, let us take for two variables a performance function which is linear. For a performance function to remain linear when the random variables are normalized, it is very easy to locate the design point, because design point is the point on the performance function which will give you the minimum distance from the origin to the performance function, because that is how design point is defined. Design point mathematically or graphically is the minimum distance of the performance function from the origin. Obviously, a line which is normal to the function will be giving you the minimum. Let us say I call this as xd, where x stands for the distance and d stands for the design point, and I call this point as d with some coordinate, let us say x1 and x2, are two variables. So, if you have a linear function, one can easily find out the point at which the distance will be minimum using a simple mathematical relationship, using an equation of a line passing through the point d. One can always find xd, and that will directly give me the safety index. So, there is no confusion if the performance function is linear. Now, let us take graphically a function which is non-linear. Now, I want to find the minimum distance of this function from the origin. One may say, sir, let us draw a tangent. Let us draw a tangent and draw a normal to the tangent, and this will be the minimum point. Now, the whole difficulty here is which is this point through which a tangent will be drawn, which will otherwise give me the minimum distance from the origin. So, locating or identifying or determining the design point on the performance function itself is actually a task. So, Haushofer-Lin method is actually centered on computing actually this point. Okay. If you are able to compute this point or locate this point graphically, finding the safety index or the reliability index is very easy, because that is going to be the minimum distance from the origin. Okay. So, identifying the or locating or estimating the design point on the performance function is actually a given task now. Okay. The method actually uses a random variable. Let us say, let the random variable be xi, where xi is actually will be x prime I, where x prime I is actually xi minus x bar I by sigma xi, where I is varying from 1 to n. Let us call this as equation number 7. Now, what actually we have done is, we have reduced the variable to have a 0 mean. So, the variable xi is reduced to x prime, which will have a 0 mean and unit standard deviation. Now, with the help of the reduced variable, original limit state function or limit state or performance function will be also converted. So, now I have to also convert the original limit state or performance function which is g x is 0 to g x slash 0, is it not? That is what I have to do. Now, the minimum distance to this function from the origin will be called as to the function from the origin is called or is named as beta HL. Beta stands for the safety or reliability index and HL stands for Haushofer-Lin. So, which is given by equation number 8, where x slash d is the minimum distance on the limit state function of the design point on the performance function with reference to the origin, of course, whereas a performance function is a modified one, okay, on the modified performance function, because the original performance function is g of x, whereas the modified one is g x prime x. So, I am using x prime d and x prime d here. Okay. So, it is a design point. Design point is also called as checkpoint, sometimes is also called as checkpoint in some literature. So, they are one and the same. Now, the whole exercise is circumscribed to find out this BHL or beta HL. So, the importance of finding beta HL can be explained with the help of linear limit state function of two variables for better understanding. So, the objective is to estimate beta HL. Okay, we will take a simple case. The limit state function is linear or performance function is linear. And number of variables are 2. So, then in that case we know z is r minus s, which is 0. The reduced variable is given by let us say r prime is r minus mu r by sigma r, which are known to us. Similarly, s prime is s minus u s sigma s. I call this equation number 10. Now, substituting for r and s from this equation in the original one, that is substituting for r and s from 10 in 9. Okay. The limit state equation can be now expressed. As sigma r r dash plus mu r minus sigma s s dash plus mu s 0. 11 or 11a, we can rearrange this equation slightly. So, sigma r r dash minus sigma s s dash plus mu r minus mu s is 0. I call this 11b. Now, in the space of reduced variables are r prime and s prime, or on the other hand z prime. Okay. In the space of reduced variable, limit state function then now can be plotted. So, I can see the plot here. Let us say I am now plotting it on the reduced variable. Let us say this is going to be my r prime, this is going to be my s prime. Okay. Let us say this is my linear limit state function, because it is r minus as a linear equation, where z is 0 or z prime is 0, that is a limit state function which is taken for the problem. Now, we know this is going to the failure state, where z is less than 0, that is assuming a negative value, because z is actually given by r minus s. Okay. And of course, this is going to be the zone where z is greater than 0. So, I can say it is a safe state. Okay. Now, what we are worrying about is the distance beta from the origin to the limit state function. Okay. That is what the worry is. So, it is actually the Haushofer-Lind reliability index with linear performance function. Okay. There is no difficulty here. Haushofer-Lind reliability index is useful to calculate the first order approximation of failure probability. Okay. So, beta HL actually is useful. The first order approximation of the probability of failure. So, probability of failure is nothing but phi of minus beta n. Equation number 12. Now, interestingly, this is nothing but the integration of the standard normal density along the ray joining the line or joining the origin and x dash of d. Now, when the limit state function is non-linear, let us say the performance function is non-linear, then locating or computing the design point and finding the minimum distance of the performance function or the limit state function from the origin actually becomes an optimization problem. Okay. So, one has got to actually find d and minimize it. So, the equation or the condition is minimize d by nothing but the root of x prime transpose x prime. So, we have to minimize this. What is the condition? Subject to the condition that, because minimization requires condition that g of x dash should be set to 0. Shinozuka has given an approximate solution for this. Shinozuka obtained an expression to obtain Haushofer-Linde index, which will tell me that it is the minimum distance. So, that is given by negative I is equal to 1 to n di derivative of this with respect to the design point by root of I call this equation number 40. So, Haushofer-Linde reliability index can be obtained with the equation given by Shinozuka. There is a negative sign here, okay, given by Shinozuka if the performance function or the limit state function is non-linear. Now, in this case, the derivatives that is derivative of g function with respect to x dash di are evaluated at design point which are x dash d1, x dash d2, x dash d3. So, we will keep on finding various design points, and various betas and minimize them. Now, the question comes here is to get the design points. Now, the design points is given by equation number 15, where alpha di is actually is, or let us say r, because there are many, or direction cosines along the coordinate axis xi. Okay. Now, in the space of original variables, we have now modified this to the different set of variables with x dash or r dash and s dash, but correspondingly in the space of original variable the desired point should be also given. Now, the design point with respect to the original variable or original space of variable is given by the following equation, which connects x dash di, which is mu xi minus alpha di sigma xi beta hl This method actually results in a linear approximation of unit state function. This method, what we just now saw, results in linear approximation of the limit state function even though the function remains nonlinear. Okay? It is an approximation. Which will on which the design points are located. Now, with the help of beta HL as obtained from the equation given earlier 14, let us say, probability of failure can be estimated. Since beta HL is known, probability of failure can be estimated as the phi function of minus beta. Now, in case if all the variables are not normally distributed, then rather it is more difficult to relate the exact probability of failure. Okay? This is true only when the variables are normally distributed. If the variables are not normally distributed, then it becomes more problematic to estimate actually the probability of failure even though you know beta HL. Okay? Rackwitz and Freiser suggested an improved technique for this. Suggested an improved method to obtain the probability of failure. They actually transformed the non-normal variables into equivalent normal variables. Okay? They actually transform the non-normal variables into equivalent normal variables. That is what they have done. Okay? We will see this in detail in the next lecture. So, in this lecture we have understood details about first order second moment method, if the performance function is linear, if the performance function is non-linear. We have also seen one more method suggested by Hasse-Ferlin, It is very easy. If the performance function is linear, one can find the design point. Design point is the point on the performance function whose distance is minimum from the origin. So, it is very easy for us to obtain a point whose distance is minimum from the origin if the point is lying on a straight line or linear function. If the performance function is non-linear, then we do some approximation to convert the space of variables to some other form and approximately convert the non-linear performance function to equivalent n number of linear functions and find design points on each one of them, and then find out distances each one of them and minimize this. That is what given by Shinozuka, which we already seen in the lecture today. However, if the variables are normally distributed, then one can easily find the performance of probability of failure if you know the reliability index given by Hasse-Fairley. If they are not normally distributed, then it becomes more complicated, because probability of failure is not then given by a simple equation like this. Okay. In that case, Rackwitz and Feisler suggested a method by which we can convert the non-normal variables to equivalent normal variables, which we will see in the next lecture. Thank you very much.